Hey everybody, Dr. A here, and in this video we're going to be providing some background information on what we call load transmission, okay? So we're going to be referencing Chapter 3 in our textbook, Structural Loading and Analysis. As you're watching this video, it'd be good if you open up your textbook and kind of follow along with me. So, from previous classes, I'm going to make a note here, from previous courses that you've taken, like in statics and mechanics of materials, we represent external reactions on coplanar or two-dimensional structures as one of what? Well, external reactions on 2D or coplanar structures typically, or actually not typically, always have either one force reaction, two force reactions, or two force reactions and one moment reaction. Okay, so again, we commonly see this in the form of a roller type of support with one force reaction, an external pin if you have two force reactions, and then a fixed connection if you have two force reactions and one moment reaction. Now, these are not the only options for external support reactions. Again, if you're referring to the textbook, table 3.1, so we're going to say table 3.1 gives several examples of coplanar structure supports. Okay, so just to refresh your memory on some of them, we have weightless cables and links, which have one force reaction. We have rollers that have one force reaction. Rockers have one force reaction. Smooth contact surfaces, and several others. So again, if you're looking at the textbook for our class, table 3.1, it has a list of several of those examples, which you could also find in most statics and mechanics of materials textbooks. Okay, now in reality, no support is purely one of these. Okay, typically, and in reality, it'll be somewhere in between. Okay, and what we mean by that is, in real life, you're not going to have a perfect frictionless roller. So, for example, if I say, e.g., we have this idea of a roller here, right? And a roller develops what? A roller develops a force reaction here. Well, when we deal with a roller, we assume that this surface is frictionless, and this little ball here, this roller, is free to just translate left and right here, okay? But in reality, that's not going to be true. There's going to be some friction here, or there's some other kind of mechanism that will give it flexibility to move left and right, but it's not going to be perfectly free to move left and right. Same thing, if I go to the other extreme with a fixed connection, right? If I have a fixed connection here, all right, and we have some loading here, well, a fixed connection tends to develop a horizontal reaction, a vertical reaction, and a moment reaction, because we say that the fixed connection is restraining movement and rotation here perfectly. It's a perfect restraint here. Well, in reality, is it really going to be a perfect restraint? Not really. I mean, this connection here may have a little bit of flexibility, just a little bit, to where it's not 100% perfectly fixed. Okay, now it may be really close to perfectly fixed, but it's not going to be 100% perfectly fixed for all kinds of loads that it might support. Okay, so this is kind of in structural analysis, this is what we want to kind of come to terms with. We're still going to model our support reactions in general as one of the support reactions found in table 3.1, but in reality, they're not going to be as perfect and as idealized as those support reactions shown in table 3.1. That's why we sometimes call those idealized models. In reality, they're not that perfect, okay? But they're in reality, we may be really close to one of those, all right? So we're going to make a note here. We're going to say we use these idealized models because they are often close to the reality of our supports. Okay. Now, what else do we typically do when we're trying to keep track of how loads are transmitted through structural systems? Well, another thing we do is we use what are called line drawings, okay? So I'm going to make a note here. We also use line drawings, which of course these little sketches I have here are examples of that, to simplify and idealize a structure when analyzing and sketching. Okay, so you want to take a look at, I'm going to say C figure 3.1 in the text. Okay, so again, instead of drawing maybe all of the details and the thicknesses of our structural members, we might often just draw them as single line segments for idealization and quick sketches. Okay, the next vocabulary word we want to make a note of is what's called a load path. Okay, so let's make a note of this. A load path is a visual representation of how applied loads acting on a structure are transmitted from one structural element to another. Okay, and again, in the textbook, we can take a look at figures 3.2 and 3.3 in the textbook to kind of get an idea of how loads are transmitted through a load path. So, for example, one very easy example of a load path could be like this. Let's say we have a frame here. And we'll just make it simple here. And let's say we have this applied load here, okay? So what is the path that this load will tend to take as it is transmitted through the structure? Well, very simply, this applied load F, okay, will get transmitted to this beam, okay? And I'm going to draw these little green arrows here. And it will get transmitted through this horizontal beam and down through these vertical columns, okay? And then it will get transmitted into these supports here, okay? And then as a response, the supports will engage reactions here, Okay, so again, this is it's the internal path the load takes throughout a structural system. Okay, now how does that load travel through the system? Well, it travels through the system through all of your structural elements, through contact points, through connection points. It's transmitted through the ideas of stress. So, if we go back to mechanics of materials and we're thinking of axial stress, flexural stress, these are all internal loads. And again, a load path is just kind of a conceptual, visual way of how an external load transmits internally through all of the connected structural members. Okay, and so part of our job as a structural engineer, when we're analyzing and just thinking about structures, is we got to think, how can we keep track of an applied load all the way through the system until it gets to its foundation or its support. Okay, so that's what I encourage you to ask yourselves whenever you're thinking about a structure. How is the applied load that the structure is supporting going to make its way through all of the structural components until it reaches the supports? Because ultimately that's what this load is trying to do. The applied load F and the effect of F, all it's trying to do is somehow get to an external support. It's trying to get to an anchor point, okay? And so again, we want to ask ourselves, how do those loads do that? What path do the loads take through the structure in order to reach a support? Okay, so that's going to conclude this video on just some of this background information. Again, you want to reference a good textbook as we go along. And before we conclude, sorry, almost forgot one thing. Okay, make a note here. We apply topics, and I kind of said this already, but I'm going to explicitly write it. We apply topics from statics and mechanics of materials to track load paths analytically. Okay, this includes the basics of, including application of equilibrium equations. Okay, so this is where we connect back to some fundamentals from statics and mechatronics, just the application of equilibrium equations as it pertains to how a load travels through our structural elements. Okay, now that's going to conclude this video. If you found this helpful, please hit like and subscribe.